Imagine a world suspended between eternal day and endless night, where one face burns under the perpetual gaze of a crimson sun, while the other shivers in the absolute cold of deep space. A silent, stark dichotomy etched onto the surface of a planet just a little larger than our own. This is Proxima Centauri b, the closest exoplanet known to humanity. It beckons from a distance that sounds deceptively small, a mere 4.2 light-years. But in the cold, hard mathematics of cosmic travel, this neighbour might as well be in another galaxy entirely, a tantalizing mirage beyond our grasp. What if the very dream of interstellar travel, a cornerstone of humanity's future, is a profound illusion? What if the universe has placed insurmountable barriers between us and even our closest celestial kin? The quest to reach Proxima Centauri b is not just a journey through space, but a profound confrontation with the limits of our engineering, our endurance, and perhaps even our understanding of physics itself. In this documentary, we will embark on an intellectual journey, dissecting the true, brutal challenges of reaching Proxima Centauri b, from the sheer, mind-bending scale of interstellar distances to the fierce, unforgiving environment of its parent star, and the fundamental technological chasms that separate our ambition from reality. If the cosmos's deepest mysteries intrigue you, then join the Terran community. Subscribe now and become part of our ongoing exploration into the furthest reaches of scientific understanding. Prepare yourselves, we begin. For millennia, humanity gazed at the stars, wondering if those distant pinpricks of light cradled other worlds, other lives. For most of that history, such thoughts remained confined to the realm of philosophy and fiction. Then, the dawn of exoplanet discovery transformed speculation into scientific pursuit, revealing a cosmos teeming with planets. Among them, one star system held particular fascination, not for its exotic beauty or immense power, but for its sheer proximity, Alpha Centauri, our closest stellar neighbour. This system, visible as a single bright point in the southern sky, is not just one star, but a magnificent triple-star ensemble. Alpha Centauri A and B form a tightly knit binary pair, two suns locked in a gravitational embrace, roughly similar to our own sun in mass and luminosity, but orbiting them at a significant distance. A full quarter of a light-year away from its brighter siblings lies a smaller, fainter star, a red dwarf. This star, almost imperceptible to the naked eye, is Proxima Centauri, the closest individual star to Earth. For decades, it remained a quiet, unassuming celestial body, a faint red ember in the vast interstellar night. Its true significance, however, would soon be dramatically revealed, igniting a spark of hope that seemed to bridge the cosmic chasm. The scientific breakthrough arrived in 2016, a culmination of meticulous observation and technological prowess. Astronomers, utilizing the high-accuracy radial velocity planet searcher, or HARPS instrument, mounted on the European Southern Observatory's 3.6-metre telescope in Chile, embarked on the Pale Red Dot project. Their goal was to detect subtle wobbles in Proxima Centauri's motion, minute gravitational tugs that would betray the presence of orbiting planets. This method, known as radial velocity detection, relies on the Doppler effect. As a star is pulled slightly back and forth by an orbiting planet, its light shifts alternately to blue or red, a telltale spectral signature. The data, painstakingly collected and analysed, unveiled something extraordinary. A distinct repeating wobble indicated a planet, roughly 1.3 times the mass of Earth, orbiting Proxima Centauri every 11.2 Earth days. This discovery sent ripples of excitement through the scientific community and the public alike. Named Proxima Centauri b, or simply Proxima b, it immediately captivated the imagination, not merely because it was a planet, but because it was the nearest exoplanet. The sheer concept of an Earth-mass world just a little over 4 light-years away transformed it from an academic curiosity into a beacon of possibility, a tangible first step towards interstellar dreams. Its mass alone was a profound catalyst for hope. At 1.3 Earth masses, Proxima b falls squarely within the category of terrestrial rocky planets, offering the tantalizing prospect of a solid surface, perhaps even mountains, valleys, and oceans. This isn't a gas giant like Jupiter or a frozen ice world, but a planet that, at least in terms of its bulk, shares a fundamental similarity with our home. Such a mass range also suggests a density compatible with a metallic core and a silicate mantle, reinforcing the notion of a geologically active world, potentially capable of sustaining an atmosphere. Further stoking the fires of optimism was its orbital position. Proxima b orbits its star at a distance of about 0.05 astronomical units, a mere 5% of the Earth-Sun distance. Despite this extreme proximity, Proxima Centauri itself is a red dwarf, significantly cooler and far less luminous than our Sun. This means that Proxima b, despite its tight orbit, resides squarely within its star's habitable zone. To clarify, the habitable zone, often colloquially termed the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot for it to boil away, and not too cold for it to freeze solid. The presence of liquid water is, of course, considered a prerequisite for life as we understand it. The confluence of these factors, its terrestrial mass, its location within the habitable zone, and most crucially its unprecedented proximity, made Proxima b an irresistible target for burgeoning interstellar projects. Visions of robotic probes, perhaps even crewed missions, began to dance in the minds of scientists and futurists. It wasn't just a distant data point, it was a potential destination, the first real opportunity to extend humanity's reach beyond the solar system. The dream became palpable, a world that might harbour oceans, might possess an atmosphere, and might even support life, all within what seemed by cosmic standards a stone's throw away. This initial intoxicating allure of Proxima b laid the foundation for decades of ambitious proposals, painting a picture of humanity's ultimate triumph over the vastness of space. It was the nearest, and therefore, it was the first target, the seemingly achievable aspiration for a species forever reaching for the stars. The discovery of Proxima Centauri b, nestled in the habitable zone of our closest stellar neighbour, ignited a firestorm of optimism. Here, a potentially rocky world, just a little heavier than Earth, seemed to beckon, a cosmic stepping stone. But the dream of interstellar travel, born from this tantalizing proximity, quickly collides with a brutal, inescapable truth: the sheer, unimaginable vastness of space. The phrase, 4.2 light-years, rolls off the tongue with deceptive ease, a number that sounds manageable, almost like a short hop in the grand scheme of the cosmos. Yet, this figure represents an abyss of distance that dwarfs any human endeavour, rendering Proxima Centauri b not a neighbour, but an alien realm infinitely far away. To truly grasp the scale, we must first understand what a light-year actually means. It is not a measure of time, but of distance. Specifically, the distance that light, the fastest entity in the universe, travels in one Earth year. Light streaks through the vacuum at approximately 300,000 kilometers per second, or about 186,000 miles per second. That's fast enough to circle the Earth over 7 times in a single second. Over the course of a year, that seemingly instantaneous speed accumulates into an astronomical stretch of space, nearly 9.46 trillion kilometers, or about 5.88 trillion miles. Multiply that colossal figure by 4.2, and we arrive at the staggering reality. Proxima Centauri b lies approximately 40 trillion kilometers, or 25 trillion miles from Earth. To put this into a more relatable context, consider the scale of our own solar system. If the Earth were reduced to the size of a marble, the Sun would be a beach ball about 25 meters away. On this scale, Pluto, at the edge of the Kuiper Belt, would be a speck of dust nearly 1.5 kilometers away. Now, to place Proxima Centauri b in this miniature model, we would need to travel over 7,000 kilometers away, the distance from New York to London, to find its equivalent. The empty space between our marble-sized Earth and this distant microscopic speck is an expanse of nothingness so profound it defies intuitive comprehension. Even within our own solar system, the journey to the outer planets takes years, not weeks. The Cassini probe took 7 years to reach Saturn, travelling at tens of thousands of kilometers per hour. New Horizons, bound for Pluto, took 9.5 years. Our fastest ever spacecraft, the Voyager 1 probe, is currently hurtling through interstellar space at a breathtaking velocity of roughly 61,000 kilometers per hour. That's over 17 kilometers per second. It has been travelling for more than 45 years, and in that time, it has only just managed to exit the Sun's heliosphere, the protective bubble of solar wind. If Voyager 1 were magically pointed directly at Proxima Centauri b from Earth and maintained its current phenomenal speed, the journey would still take approximately 75,000 years. 75 millennia. To put that in human terms, that's a journey longer than the entirety of recorded human civilization. Stretching back to the earliest cave paintings, it's a duration that would see countless generations born, live, and die aboard the spacecraft, long before even a faint glimmer of Proxima Centauri b became visible to the naked eye. This immense timescale immediately highlights the first, most fundamental barrier to interstellar travel: time itself. Any mission using current or even near-future technology would represent not just a voyage, but a generational odyssey, an act of faith spanning countless lifetimes. The implications for crew, resources, and the very purpose of the mission are staggering. What kind of society could endure such a journey? What knowledge would be lost or gained over 75,000 years? The challenge isn't merely about building a fast ship. It's about building a self-sustaining civilization capable of maintaining its purpose and cohesion for an epoch. And this 75,000-year estimate is for a probe travelling at a speed achieved through a gravity-assist slingshot around Jupiter, a one-off acceleration event not easily repeatable for a sustained journey or a heavier spacecraft. To genuinely attempt to reach Proxima Centauri b within a more human timeframe, say a few centuries or even a few decades, would require accelerating a spacecraft to a significant fraction of the speed of light. Even just 10% of the speed of light, or 0.1 c, would reduce the travel time to a still daunting 42 years. While this might seem achievable, the energy required to reach such velocities is mind-boggling, a challenge that transcends current engineering capabilities and ventures into realms of theoretical physics. Consider Einstein's famous equation, E=mc2, which reveals the profound relationship between mass and energy. To accelerate even a small mass, like a robotic probe, to a substantial fraction of the speed of light demands an exponential input of energy. Our most powerful rockets today, propelled by chemical reactions, can achieve speeds of mere tens of kilometers per second. To reach 0.1 c, we would need to generate kinetic energy equivalent to many thousands, if not millions, of times the total annual energy consumption of all humanity. This is not simply a matter of building a bigger fuel tank. It's a fundamental limitation rooted in the physics of propulsion. Chemical rockets simply cannot carry enough fuel to achieve such speeds. Even the most advanced theoretical fusion or antimatter drives, which promise vastly higher efficiencies, still face monumental technical hurdles in fuel production, containment, and energy conversion. The difficulty lies in the tyranny of the rocket equation, a fundamental principle of astrodynamics. This equation dictates that for every increment of velocity you want to add, you need a disproportionately larger amount of fuel. To accelerate to a significant fraction of light speed, the vast majority of your spacecraft's mass would have to be fuel, making the endeavour impractical, if not impossible, with any known propulsion system. The energy required to accelerate the fuel itself, which then burns to accelerate the payload, creates a runaway exponential curve. We are not just pushing a car, we are trying to accelerate a vehicle whose primary purpose is to carry the energy needed to accelerate itself. Even if a technological miracle allowed us to achieve such speeds, the sheer distance still presents further complications. Navigating a course over 40 trillion kilometers with pinpoint accuracy, avoiding microscopic debris that could vaporize a spacecraft at relativistic velocities, and maintaining systems for decades in the harsh vacuum of interstellar space are challenges beyond anything we currently face. The empty space between stars is not truly empty. It is filled with trace amounts of gas, dust, and high-energy cosmic rays. At hundreds or thousands of kilometers per second, even a grain of sand becomes a lethal projectile capable of catastrophic damage. The perceived proximity of Proxima Centauri b, therefore, is a cruel illusion, masking an insurmountable chasm defined by time, energy, and the relentless, unforgiving scale of the cosmos. Our nearest neighbour is, in essence, as far away as forever. The intoxicating allure of Proxima Centauri b, our closest stellar kin, quickly fades when confronted with the unyielding reality of interstellar velocity. The 4.2 light-years that separate us from this promising exoplanet are not just a measure of distance, but a cosmic stopwatch, ticking out durations that dwarf human civilization and expose the profound limitations of our current technological prowess. To truly appreciate this speed barrier, we must differentiate between merely escaping Earth's gravitational well and actually traversing the unfathomable void between star systems. Our most powerful rockets today, like the Saturn V that launched the Apollo missions, can achieve speeds of around 11 kilometers per second, enough to break free of Earth's gravity and begin an interplanetary journey. But this is a crawl compared to what's needed. The New Horizons probe, which successfully visited Pluto, reached a top speed of approximately 16 kilometers per second, making it the fastest object ever launched from Earth. Yet, even at that incredible velocity, its journey to Pluto took nearly a decade. To even escape the Sun's gravitational influence entirely, to truly enter the interstellar medium as Voyager 1 has, requires an even greater velocity, achieved through powerful slingshot maneuvers around gas giants. These are feats of interplanetary engineering, not interstellar travel. True interstellar travel, the kind that might one day carry humanity or its emissaries to another star system within a reasonable time frame, demands speeds that dwarf even these record-breaking achievements. We're not talking about tens of kilometers per second, but tens of thousands, or even hundreds of thousands of kilometers per second, itself. To clarify, the speed of light in a vacuum, approximately 300,000 kilometers per second, is the ultimate cosmic speed limit, as dictated by Einstein's theory of special relativity. While science fiction often conjures images of faster-than-light travel, or FTL, current understanding of physics suggests this remains firmly in the realm of impossibility. Therefore, the goal for any realistic interstellar mission is to approach, but never quite reach, this cosmic speed barrier. Even achieving a mere 10% represent an unprecedented leap in human engineering. At this velocity, the journey to Proxima Centauri b would theoretically take approximately 42 years. While still a multi-decade endeavour, this time frame begins to fall within the realm of human lifespan, making a single-generation mission conceivable, at least in principle. However, the energy cost associated with accelerating even a small spacecraft to such velocities is so astronomical that it defies all current and foreseeable technological capabilities. This is where the infamous tyranny of the rocket equation becomes a crushing reality. The rocket equation, a fundamental principle of aerospace engineering, dictates a non-linear relationship between the final velocity a rocket can achieve and the amount of propellant it must carry. In essence, for every increment of speed you wish to gain, you need an exponentially larger amount of fuel. The vast majority of a rocket's mass, even at launch from Earth, is not its payload, but its fuel. To achieve even a fraction of light speed, the mass ratio, the ratio of the total mass of the rocket at launch to its final mass after all fuel is expended, would become impossibly large. You would need to carry an amount of fuel that weighs more than the entire Earth, or even a small star, just to accelerate a relatively small payload to 0.1 c. This isn't an engineering hurdle that can be solved by simply building a bigger engine. It's a thermodynamic wall embedded in the very fabric of physics. Consider the kinetic energy equation. E 1 + 2 mv2. Even if m, the mass of our spacecraft, were optimized to be as small as possible, perhaps a mere gram-scale probe, the v, or velocity, raised to the power of 2, means that the energy required grows explosively as we approach the speed of light. To accelerate a mere kilogram to 0.1 c, the kinetic energy involved would be equivalent to that released by many large nuclear weapons. To scale this up to a crude spacecraft, even one stripped down to its bare essentials, would require an energy output exceeding the entire annual electricity production of all human civilization by thousands of times. Our current power generation capabilities are simply insufficient to even contemplate such a feat. This is why scientists and engineers constantly explore theoretical propulsion systems that promise greater efficiency. Chemical rockets, relying on the exothermic reactions of propellants, are inherently limited by the energy density of their fuel. Ion thrusters, which accelerate charged particles to very high velocities using electric fields, are incredibly fuel efficient, but produce only a minuscule amount of thrust. They can accelerate spacecraft to impressive speeds over very long durations, but the time required to reach a significant fraction of C would still be prohibitive for an interstellar journey. Nuclear thermal rockets offer an improvement by using a nuclear reactor to heat propellant to extreme temperatures, but still fall far short of the velocities needed. More exotic concepts like nuclear fusion rockets represent a tantalizing step forward. Fusion reactions, which power our Sun, release vastly more energy per unit mass than fission or chemical reactions. A fusion rocket could theoretically achieve exhaust velocities far greater than any current technology, potentially pushing a spacecraft to a few % of the speed of light. However, the engineering challenges are immense. Sustained, controlled fusion reactions are still a dream on Earth, let alone within a compact, reliable propulsion system. Furthermore, even with fusion, the sheer amount of reaction mass required to accelerate a significant payload to a meaningful fraction of C still poses a monumental logistical and physical challenge, once again bowing to the tyranny of the rocket equation. The most efficient theoretical propulsion system known to physics is antimatter annihilation. When matter and antimatter collide, their entire mass is converted into energy, following Einstein's EEMC2 with near-perfect efficiency. This could provide the necessary thrust to achieve truly relativistic speeds, perhaps even 0.5 C or higher, potentially reducing the Proxima Centauri B journey to a mere 8 or 9 years for Earthbound observers. However, the hurdles here are even more staggering. Producing antimatter is incredibly energy-intensive and expensive. Estimates suggest quadrillions of dollars per gram, if even possible on a large scale. Furthermore, storing antimatter, which instantly annihilates upon contact with ordinary matter, is a challenge that borders on science fiction. We can currently only produce picograms of antimatter for short durations in laboratory settings, a quantity utterly insufficient for interstellar propulsion. Beyond the energy and fuel requirements, the very act of travelling at relativistic speeds introduces another profound and often misunderstood barrier: time dilation. A consequence of Einstein's special relativity, time dilation means that for an observer moving at e, time will pass more slowly relative to a stationary observer. So, for the crew aboard a starship hurtling towards Proxima Centauri b at, say, 0.9 C, the subjective experience of the journey would be shorter. For them, a 4.2 light-year trip might feel like only a couple of years, but for those left behind on Earth, decades would still pass. This paradox doesn't shorten the objective distance or the time it takes for information to traverse it. It merely warps the experience of time for the travellers. This means that even if a crew could make the journey in a subjectively short time, any communication with Earth would still be delayed by the 4.2 years it takes for light to travel one way. A simple hello would arrive years later, and a response would take another 4.2 years. Real-time interaction, essential for any sense of connection or even mission support, becomes impossible. Furthermore, any return journey would face the same time dilation, effectively meaning that upon returning, the crew would find Earth centuries or even millennia ahead of their own subjective timeline, a profound form of temporal displacement. In essence, the speed barrier is not just a technological hurdle, it is a fundamental cosmic constant. The vastness of space, coupled with the unyielding laws of physics governing mass, energy and time, creates an almost impenetrable shield around Proxima Centauri. Be it dictates that to reach our nearest celestial neighbour, we must either embark on a journey that spans countless generations, a slow drift across an ocean of emptiness, or achieve a level of propulsion technology that currently exists only in the realm of theoretical speculation, demanding breakthroughs that rewrite the very rulebook of the universe. The cosmic stopwatch reveals that Proxima Centauri b, though close, demands a sacrifice of time and energy that humanity is currently utterly incapable of paying. Even if humanity could somehow conquer the mind-bending distances and achieve the impossible velocities required to reach Proxima Centauri b, the promise of a nearby, potentially habitable world would quickly give way to a far harsher reality. The alluring proximity of Proxima b is inextricably linked to its parent star Proxima Centauri, a celestial body whose very nature renders its habitable zone a crucible of hostile energy, the red dwarf's relentless rage. Proxima Centauri is a red dwarf, a class of stars far more common than our Sun, comprising roughly 70% of all stars in the Milky Way. These stars are significantly smaller and cooler than our yellow-white sun, emitting primarily in the infrared spectrum. They burn their nuclear fuel at a much slower, more efficient rate, granting them incredibly long lifespans, potentially trillions of years, far outliving the projected lifespan of our own sun. On the surface, this might sound like an ideal scenario for the development and evolution of life. Billions, even trillions, of years of stable energy output. However, this seemingly tranquil longevity masks a profoundly violent truth about these diminutive suns. Despite their cool temperatures and low luminosity, red dwarfs are notoriously tempestuous, especially in their early stages, but continuing their volatile behavior throughout much of their long existence. Their convective interiors, where material constantly churns from core to surface, generate powerful, tangled magnetic fields. These fields frequently snap and reconnect with explosive force, releasing colossal amounts of energy in what are known as stellar flares. These are not merely minor solar hiccups. For a red dwarf, a flare can release energy equivalent to the entire star's normal output over several hours, dwarfing even the most powerful flares ever witnessed from our sun, relative to its size and luminosity. The impact of these flares on any closely orbiting planet, like Proxima Centauri b, is catastrophic and unrelenting. While our sun experiences flares periodically, Proxima Centauri can unleash such events multiple times a day, sometimes for hours on end, creating an almost continuous barrage of high-energy radiation. These flares manifest as sudden, dramatic increases in X-ray and ultraviolet radiation, alongside torrents of highly energetic charged particles, primarily protons and electrons, ejected into space at immense speeds. For a planet orbiting so close to its star, Proxima b is just 7.5 million kilometers away, less than 5% of Earth's distance from the Sun. There is virtually no escape from this constant cosmic assault. The primary devastating consequence of this incessant bombardment is atmospheric stripping. Any planet hoping to harbour liquid water, and thus life, requires a stable, protective atmosphere. The high-energy X-rays and ultraviolet radiation from Proxima Centauri's flares can photodissociate atmospheric molecules, breaking them apart into their constituent atoms. Simultaneously, the powerful stream of charged particles, often referred to as a stellar wind or coronal mass ejection, can physically batter these atmospheric particles, accelerating them to escape velocity and effectively blowing them away into space. This process, known as sputtering and thermal escape, would, over geological timescales, relentlessly erode any primordial atmosphere Proxima b might have possessed, regardless of how thick it once was. Consider Earth's own atmosphere and magnetic field, which act as a formidable shield. Our planet's powerful magnetosphere deflects the sun's solar wind, channeling charged particles towards the poles, where they create the aurora. Our thick atmosphere then absorbs most of the harmful UV and X-ray radiation, preventing it from reaching the surface. Proxima b, however, may not be so fortunate. If its atmosphere has been largely stripped away, or is too thin to begin with, its surface would be directly exposed to the full, raw fury of its star's flares. Even if Proxima b possesses its own strong magnetic field, a prerequisite for deflecting charged particles, the sheer intensity and frequency of Proxima Centauri's flares could overwhelm it, allowing devastating levels of radiation to penetrate. The implications for life on the surface are dire. Intense bursts of X-ray and ultraviolet radiation are highly destructive to organic molecules, including DNA. Such radiation acts as a powerful mutagen, causing widespread damage to genetic material, making it incredibly difficult for complex life forms, particularly those relying on photosynthesis or fragile cellular structures to evolve or survive. Any hypothetical life on Proxima b would need to exist either deep underground, shielded by kilometers of rock, or possess extraordinary unknown mechanisms for radiation resistance and repair. Surface life, as we know it, would be continuously sterilized by the torrents of high-energy particles and lethal electromagnetic radiation. Moreover, the flares dramatically impact the habitability of the planet's surface, not just in terms of radiation, but also temperature. While Proxima b resides in the habitable zone based on its average stellar flux, powerful flares would cause sudden dramatic heating events. These could lead to rapid vaporization of surface water, if any exists, or trigger runaway greenhouse effects that boil away oceans into space. Such extreme variability in surface conditions would present an additional overwhelming challenge for life. Imagine a world where the weather forecast isn't just rain or sunshine, but unpredictable planet-wide sterilization events occurring multiple times a week. Observational data from telescopes like NASA's Hubble Space Telescope and Transiting Exoplanet Survey satellite, TESS, has confirmed the violent nature of Proxima Centauri. Studies have shown that Proxima Centauri flares are indeed more powerful relative to its bolometric luminosity and more frequent than those of our Sun. Some flare events observed have been hundreds of times stronger than the most extreme events our Sun has produced. These findings paint a bleak picture for the long-term atmospheric stability and surface biology of Proxima Centauri b, suggesting that the initial optimistic assessment of its habitability may have been premature, or at least significantly oversimplified. Therefore, even if we could overcome the immense challenges of interstellar distance and speed, any mission to Proxima Centauri b would immediately confront a planet fundamentally reshaped and actively threatened by its own star. A spacecraft would require unprecedented levels of radiation shielding to protect its sensitive electronics and any human crew over the course of the journey, and then even more robust protection upon arrival. Landing on Proxima b would mean descending onto a world likely bathed in lethal radiation, constantly pummeled by stellar storms, and perhaps devoid of a protective atmosphere, rendering the dream of a new home a grim, irradiated wasteland. The red dwarf's rage is not merely an inconvenience, it is a cosmic barrier, turning a potentially welcoming world into an inferno for complex life. Even if the colossal gulf of interstellar space and the relentless fury of a red dwarf's flares could somehow be overcome, Proxima Centauri b presents another profound, almost alien barrier to habitability and exploration: the stark, unforgiving reality of tidal locking. This phenomenon, born from the gravitational embrace between a star and a closely orbiting planet, dictates that Proxima b does not rotate as our Earth does. Instead, one face of the planet is locked in perpetual unwavering daylight, forever illuminated by its crimson sun, while the other remains plunged into an eternal frigid night. To understand tidal locking, consider our own moon. It always shows the same face to Earth. This is because Earth's gravity has stretched and slowed the moon's rotation over billions of years until its rotation period perfectly matched its orbital period. Proxima Centauri b, orbiting its star at an incredibly close 7.5 million kilometers, about 20 times closer than Earth is to the Sun, experiences these gravitational forces with far greater intensity. Its entire rotational dynamic has been arrested, leaving it in a state of permanent stellar embrace. This creates a world of fundamental dramatic contrasts, a cosmic schism etched onto its very surface. Imagine standing on the day side of Proxima b above, Proxima Centauri, though a red dwarf would loom significantly larger than our Sun appears from Earth, a fiery, unmoving crimson disk dominating the sky. This side of the planet would be subject to continuous relentless stellar radiation, a never-ending inferno. Without a day-night cycle to allow for cooling, temperatures on the substellar point, the exact spot directly beneath the star, could soar to unimaginable extremes. Even if the star itself is cooler than the Sun, the accumulated non-dissipated energy over eons would create a superheated environment. Scientific models suggest that temperatures could easily reach hundreds of degrees Celsius, potentially hot enough to melt rock and create vast, shimmering lakes of lava on its surface, especially if it lacked a substantial heat-distributing atmosphere. Any water on this side would have long since boiled away into space, a victim of both the continuous heat and the stellar flares discussed previously. The landscape would be a desiccated, blazing wasteland, constantly under the gaze of a star that never sets. Now, traverse the planet to the night side. Here, the experience would be diametrically opposite. Proxima Centauri would be completely absent from the sky, hidden forever behind the planet's curvature. This side would be shrouded in perpetual absolute darkness, a realm of profound and unyielding cold. With no stellar energy input, temperatures would plummet to hundreds of degrees below zero, approaching the cryogenic depths of interstellar space. Any atmospheric gases, such as nitrogen or carbon dioxide, would likely freeze out of the sky, forming vast continent-sized glaciers of solid air and snow. Water, if any survived the stellar flares, would be locked into immense impenetrable ice sheets, stretching from horizon to horizon, perhaps kilometers thick. This would be a silent, frozen mausoleum, a stark reminder of the planet's unforgiving cosmic isolation. Between these two extremes lies the terminator zone, a narrow circular band where perpetual twilight reigns. Here, the star would hover perpetually on the horizon, creating an endless sunrise or sunset. This slim ribbon of land, caught between the inferno of the dayside and the deep freeze of the nightside, is often considered the only potential refuge for liquid water, and, hypothetically, for life. However, even this temperate zone would be a place of unimaginable meteorological violence, a chaotic battleground of super winds. The immense temperature differential between the scorching dayside and the freezing nightside would drive powerful, planetary-scale atmospheric circulation. Hot, expanding air from the dayside would rush towards the cold, dense, vacuum-like conditions of the nightside, creating relentless, hurricane-force winds that would sweep across the terminator. These are not merely strong breezes. These are persistent, hypersonic gales, potentially reaching thousands of kilometers per hour, capable of scouring the surface bare, eroding rock, and making any stable surface environment impossible. Such winds, known as geostrophic winds, would create vast swirling vortexes and colossal storm systems that dwarf anything seen on Earth. If Proxima b managed to retain a substantial atmosphere despite the flares, this atmosphere would become a dynamic, turbulent river of gas. The dayside might feature a permanent thick cloud deck born from evaporating surface water that is then carried by the winds to the nightside. As this hot, moist air encounters the frigid temperatures of the nightside, it would condense and freeze, raining down as endless blizzards of snow or frozen atmospheric gases, depositing immense ice caps. This continuous cycle would mean that the planet's atmosphere might largely freeze onto its nightside, slowly depleting the dayside, only to be sublimated and driven back again over geological timescales. This creates a powerful negative feedback loop, potentially leading to a nearly airless dayside and a nightside choked with frozen air. The existence of liquid water, even in the habitable zone, becomes incredibly precarious under these tidally locked conditions. Any surface water might form a global ocean that remains perpetually frozen on the nightside, while simultaneously evaporating on the dayside. The terminator zone could harbour narrow bands of liquid water, but they would be constantly battered by the super winds, making them incredibly turbulent and inhospitable. Furthermore, the intense atmospheric circulation could lead to massive storms that transport heat unevenly, causing unpredictable and extreme weather fluctuations even within the supposedly temperate band. Such a dynamic, constantly violent environment would pose an existential challenge to any organism attempting to thrive on the surface. Therefore, Proxima Centauri b, far from being a tranquil, Earth-like haven, is a world of unrelenting extremes. Its tidally locked nature means that any life, or any human settlement, would have to contend with a planet fundamentally divided. A blazing inferno on one side, a frozen abyss on the other, and a perpetually storm-lashed twilight zone in between. This dramatic dichotomy is not merely an aesthetic curiosity. It is a fundamental environmental barrier that makes the surface of Proxima b profoundly hostile, even without considering the stellar flares. The habitable zone becomes a misnomer, a purely thermal calculation that fails to account for the dynamic, often destructive realities of planetary mechanics around a red dwarf star. The dream of reaching this nearest exoplanet thus confronts not just distance, but a world so utterly alien in its fundamental conditions that survival on its surface would be an unprecedented biological and engineering challenge. Achieve the impossible velocities and navigate the extreme conditions of a tidally locked world, a more insidious, pervasive threat awaits: radiation. Far beyond the visible light and heat, the cosmos is a violent sea of high-energy particles and electromagnetic waves, an invisible killer that relentlessly chips away at both technology and biology. This omnipresent hazard, both from the interstellar void and from Proxima Centauri itself, poses perhaps the most fundamental and least understood barrier to reaching our nearest exoplanet. We have previously touched upon the fury of Proxima Centauri's flares, those sudden, dramatic bursts of X-ray and ultraviolet radiation, accompanied by torrents of charged particles. While these events are indeed catastrophic, their danger extends far beyond mere bursts. Proxima Centauri, like all stars, constantly emits a stellar wind, a stream of charged particles flowing outward from its corona. For red dwarfs, particularly active ones like Proxima Centauri, this stellar wind is often far more dense and energetic than our Sun's, even during quiescent periods. A planet like Proxima b, orbiting so close to its star and likely lacking a substantial protective atmosphere, would be continuously bathed in this torrent. Any unshielded spacecraft, lander, or even human settlement on Proxima b would face a persistent high-dose radiation environment, a perpetual low-level bombardment that would quickly degrade materials and prove lethal to biological systems over time. But the radiation threat isn't confined to the immediate vicinity of a star. The vast, seemingly empty expanse of interstellar space itself is a treacherous environment, a cosmic shooting gallery of high-energy particles known as galactic cosmic rays, or GCRs. These are not merely solar wind particles. GCRs are extremely energetic atomic nuclei, mostly protons, but also heavier elements, accelerated to nearly the speed of light by cataclysmic events across the galaxy, such as supernovae and the powerful jets emanating from supermassive black holes. Unlike the relatively predictable solar flares, GCRs arrive from all directions, an isotropic hail of microscopic bullets that can penetrate deep into matter. For a spacecraft, the continuous bombardment by GCRs presents a profound engineering challenge. These high-energy particles can cause single-event upsets, SEUs, in microelectronics, momentary glitches or permanent damage to computer chips, memory, and control systems. Over a multi-decade or multi-century journey, the cumulative effect of these SEUs would be devastating, leading to system failures, data corruption, and eventually the complete breakdown of critical navigation, communication, and life support systems. Imagine a ship's autopilot sporadically failing, or its life support monitors giving erroneous readings over and over again for decades. Such a journey would quickly devolve into an unmanageable cascade of technical malfunctions, jeopardizing the entire mission. For any human crew, the biological threat is even more terrifying. On Earth, our thick atmosphere and robust magnetic field shield us from the vast majority of cosmic radiation. Even astronauts on the International Space Station, orbiting within Earth's magnetosphere, experience significantly higher radiation doses than on the surface, increasing their lifetime cancer risk. But an interstellar journey would expose a crew to GCRs with virtually no planetary protection. These highly penetrating particles rip through human tissue, ionizing atoms and molecules, causing direct damage to DNA. The immediate acute effects of high-dose radiation exposure include radiation sickness, characterized by nausea, vomiting, fatigue, and immune system suppression. However, the true danger of interstellar travel lies in the chronic, long-term effects of prolonged low-dose exposure. Even if the dose rate doesn't cause immediate incapacitation, the cumulative damage over decades would be profound. Increased risk of various cancers, leukemia, solid tumors, is almost guaranteed. Beyond cancer, studies indicate a heightened risk of cataracts, damage to the central nervous system leading to cognitive deficits, memory loss, and even an accelerated onset of neurological disorders like Alzheimer's and Parkinson's. The cardiovascular system is also susceptible, with increased risk of heart disease due to inflammation and damage to blood vessels. Reproductive health would be severely compromised, with potential infertility and increased risks of birth defects in subsequent generations if such a mission were multi-generational. The core problem with mitigating this radiation is the sheer mass penalty of conventional shielding. Materials like lead, steel, or even water can absorb radiation, but to provide adequate protection against GCRs for decades would require shields so thick and heavy that no current or foreseeable propulsion system could accelerate them to interstellar velocities. Carrying thousands of tons of shielding mass, on top of the spacecraft, fuel and payload, would render the mission impossible under the tyranny of the rocket equation. Furthermore, dense shielding presents its own paradox. When extremely high-energy GCRs strike heavy atomic nuclei in a shield, they can fragment those nuclei, producing a shower of secondary radiation, neutrons, protons, and other particles that can be even more damaging than the original cosmic ray. This phenomenon, known as spallation, means that a poorly designed shield can actually make the radiation environment worse inside the spacecraft. Scientists are exploring active shielding concepts, such as generating powerful magnetic fields around the spacecraft to deflect charged particles, or creating plasma shields that could ionize and slow down incoming radiation. While theoretically promising, these technologies require immense amounts of power to generate and maintain, far beyond what any current spacecraft can provide, and are still largely confined to conceptual drawings and laboratory experiments. They represent a fundamental leap in energy generation and control, technologies that are decades, if not centuries, away from practical application. The long duration of any plausible interstellar journey, decades for a hypothetical 0.1c mission, or millennia for a slower, more realistic one, exacerbates the radiation problem beyond anything we've tackled in Earth orbit or even lunar missions. It's not about surviving a single solar flare or a brief trip through the Van Allen belts. It's about enduring a relentless, invisible siege that continuously degrades matter and slowly poisons biology. The cumulative dose over such immense timescales would be overwhelming, a slow, inevitable march towards cellular chaos and systemic failure. In essence, the cosmic void between stars is not an empty, benign highway, and even the habitable zone of Proxima Centauri is a cauldron of stellar fury. Interstellar and stellar radiation represent a two-pronged existential threat that demands not just advanced engineering, but potentially a rethinking of human biology or a fundamental alteration of physics itself. Without a breakthrough in radiation shielding or propulsion that defies current understanding, Proxima Centauri b, though our closest stellar neighbour, will remain forever beyond our reach, guarded not just by distance, but by an invisible, ceaseless torrent of lethal energy. Even if we could hypothetically overcome the crushing distances, the hostile stellar environment, and the ceaseless cosmic radiation, the most formidable barrier to reaching Proxima Centauri b remains firmly rooted in our current scientific and engineering capabilities. The engineering impossible, the fundamental technological chasm separating our ambition from reality. Humanity's dream of interstellar travel hinges on breakthroughs in propulsion that are not merely incremental improvements, but paradigm shifts requiring either a revolution in physics or access to resources on a scale currently unimaginable. Our current spaceflight technology, while impressive for interplanetary exploration, is utterly inadequate for interstellar journeys. Chemical rockets, the workhorses of modern spaceflight, operate by expelling hot gas at high velocity. Their fundamental limitation, as previously discussed through the tyranny of the rocket equation, lies in the energy density of their fuel and the efficiency of converting that energy into thrust. To accelerate even a small probe to a fraction of light speed using chemical rockets would require a fuel tank larger than a planet, a logistical absurdity. We simply cannot carry enough fuel to achieve the necessary velocities. This stark reality pushes scientists to explore theoretical propulsion systems that promise vastly greater efficiencies. One of the most frequently discussed concepts is the fusion rocket. Unlike chemical rockets that rely on burning fuel, fusion rockets aim to harness the power of nuclear fusion, the same process that powers stars. By fusing light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, an immense amount of energy is released, which could then be used to heat a propellant to extreme temperatures and expel it at very high velocities, generating far greater thrust and exhaust speeds than chemical reactions. Theoretically, a well-designed fusion rocket could achieve exhaust velocities of Zeon, potentially cutting the Proxima Centauri b journey time down to decades, rather than millennia. However, the engineering hurdles for fusion propulsion are monumental. Controlled nuclear fusion, generating more energy than it consumes, remains one of the holy grails of energy research on Earth. Despite decades of intense effort and billions of dollars invested in projects like ITER, International Thermonuclear Experimental Reactor, we are still years away from achieving sustained net positive energy fusion power plants. Translating this complex, large-scale and incredibly sensitive technology into a compact, reliable and powerful propulsion system capable of operating autonomously for decades in the harsh environment of space adds layers of complexity that currently seem insurmountable. Fuel acquisition and storage also present challenges. While deuterium is relatively abundant in seawater, tritium is scarce and radioactive, requiring either complex on-site production or massive quantities to be carried from Earth. The containment of a multi-million-degree plasma, generation of powerful magnetic fields, and efficient conversion of fusion energy into directed thrust are problems that push the absolute limits of material science and plasma physics. Another theoretical contender is the antimatter drive. This concept leverages the most efficient energy conversion process known, the annihilation of matter and antimatter. When a particle meets its antiparticle, their entire mass is converted into pure energy in the form of high-energy gamma rays. This energy could then be directed to heat a propellant or directly produce thrust. An antimatter drive offers the highest theoretical specific impulse, a measure of rocket efficiency, of any known propulsion method, potentially enabling spacecraft to reach a significant fraction of light speed, perhaps even 50% or more, dramatically reducing travel times to Proxima b to under a decade for Earthbound observers. But the challenges here are even more daunting than fusion. Producing antimatter is incredibly inefficient and energy-intensive. Current methods at facilities like CERN's antiproton decelerator can create only minute quantities, picograms, of antimatter, requiring vastly more energy input than output. To fuel an interstellar mission would require kilograms, perhaps even tons of antimatter, a quantity so immense that it is currently beyond the realm of practical science. Furthermore, storing antimatter is an extraordinary feat. It must be kept in a perfect vacuum, suspended by magnetic fields, as any contact with ordinary matter would result in immediate violent annihilation. Developing robust, long-term, and scalable storage solutions for antimatter is a technological hurdle that we are nowhere near overcoming. The sheer energy cost, the incredibly low production rates, and the profound storage difficulties make antimatter propulsion a distant dream, requiring a revolution in particle physics and manufacturing on an industrial planetary scale. Even more ambitious concepts like the Bussard ramjet attempt to circumvent the fuel problem entirely. Proposed by physicist Robert W. Bussard in 1960, the ramjet concept envisions a colossal magnetic funnel, perhaps thousands of kilometers in diameter, scooping up interstellar hydrogen as the spacecraft travels. This collected hydrogen would then be compressed and used as fuel for a fusion reactor, continuously propelling the ship without needing to carry all its fuel from Earth. This free fuel idea is incredibly attractive, potentially allowing continuous acceleration and theoretically enabling speeds close to the speed of light. However, the Bussard ramjet faces its own set of seemingly insurmountable problems. The density of interstellar hydrogen, even in relatively dense regions, is incredibly low, only a few atoms per cubic centimetre. To collect enough fuel to power a fusion reactor, the magnetic funnel would need to be truly colossal, an engineering feat far beyond our capabilities. The drag created by scooping up this hydrogen, even at low densities, would be immense at relativistic speeds, potentially cancelling out much of the thrust generated. Furthermore, the efficiency of collecting, compressing, and fusing such diffuse matter, while also dealing with the radiation generated by the fusion process, adds layers of complexity that have kept the Bussard ramjet firmly in the realm of theoretical speculation, a grand concept facing countless practical impossibilities. Beyond propulsion, the engineering challenges extend to every single system aboard an interstellar spacecraft. Life support systems would need to be perfectly closed-loop, recycling every atom of water, every molecule of oxygen, and every nutrient for decades or centuries without failure. The reliability required for such systems, operating without resupply or external repair, is exponentially greater than anything we have ever built. Waste disposal, atmospheric regeneration, food production, all must function flawlessly in a self-contained, completely isolated ecosystem. Our longest duration space missions on the ISS rely on frequent resupply missions from Earth. An interstellar craft would be a truly independent artificial world. Communication systems also present an enormous hurdle. Sending and receiving signals over 4.2 light-years means that any message would take 4.2 years to reach its destination. For a crewed mission, this translates into a profound isolation from Earth, with no possibility of real-time assistance or conversation. The data bandwidth would also be incredibly limited across such vast distances, meaning that complex scientific data or high-resolution images would take an excruciatingly long time to transmit. potentially arriving after the mission itself had ended. In essence, the technological barriers to reaching Proxima Centauri b are not merely about making existing systems a little better or a little faster. They demand fundamental breakthroughs in physics, materials science, energy generation, and autonomous systems that are currently beyond our grasp. These are not problems that can be solved with a bigger budget or a clever redesign. They require entirely new scientific paradigms. Until humanity unlocks methods of propulsion that defy the current tyranny of the rocket equation, or discovers entirely new energy sources and shielding capabilities, Proxima Centauri b will remain tantalizingly out of reach, a cosmic prize guarded by the ultimate barrier, the engineering impossible. Faced with the insurmountable distances and the cosmic speed limit, the concept of a generation ship emerges as a desperate, yet captivating theoretical solution to interstellar travel. If we cannot go faster, the thinking goes, then we must go longer. A generation ship is a colossal, self-contained ark designed to sustain multiple generations of humans and their ecosystem through centuries or even millennia of travel, with the original crew long dead before the destination is reached. It represents not just an engineering feat, but a profound social and biological gamble, asking humanity to embark on a journey from which no one who begins it will live to see its end. The design of such a vessel would stretch the limits of engineering to their absolute breaking point. This isn't merely a large spacecraft, it's a miniature artificial world. A closed-loop biosphere designed to replicate Earth's life-sustaining processes with flawless precision for an epoch. Every breath of air, every drop of water, every calorie of food must be recycled, regenerated, and sustained internally. Imagine a complex interwoven tapestry of bioreactors, hydroponic farms, and atmospheric scrubbers, all operating in perfect harmony, with no possibility of resupply from Earth. The failure of even a single critical component, a specific strain of nitrogen-fixing bacteria in the soil, a crucial filtration membrane, or a bioluminescent algal culture, could trigger a cascading ecological collapse, dooming the entire mission. Our current experience with closed-loop systems, even on the scale of the International Space Station or Biosphere 2, demonstrates the immense fragility and complexity involved. Errors, breakdowns, and unexpected biological shifts are not just possibilities, they are inevitabilities over such vast timescales, demanding a level of self-repair and resilience far beyond anything we can currently envision. Beyond the ecological complexities, the biological challenges for the human crew are equally daunting. Previous discussions highlighted the relentless barrage of interstellar radiation. On a generation ship, this isn't a temporary exposure, it's a continuous multi-generational assault. Even with advanced shielding, a low but persistent dose of galactic cosmic rays would be unavoidable. Over centuries, this would lead to a significant increase in cancer rates, cardiovascular issues, and neurological degeneration across successive generations, but more insidiously, it would affect the very genetic makeup of the population. Radiation acts as a mutagen, causing damage to DNA that can lead to increased rates of genetic mutations. While some mutations are benign, or even beneficial, a continuous accumulation of deleterious mutations could lead to a decline in overall population health, fertility issues, and an increased susceptibility to disease, potentially compromising the long-term viability of the human lineage aboard the vessel. Furthermore, a generation ship, by its very nature, would begin with a relatively small founding population. This immediately introduces the profound risk of genetic bottlenecking and genetic drift. With a limited gene pool, inbreeding becomes an unavoidable concern over many generations, leading to a decrease in genetic diversity. This reduction in diversity makes the population highly vulnerable to new diseases or environmental stresses, as there are fewer genetic variations to confer resistance or adaptability. Recessive genetic disorders, which might be rare and hidden in a large diverse population on Earth, could become rampant within the confined and isolated gene pool of a starship, threatening the physical and mental health of the entire community. Maintaining a healthy, viable genetic stock over hundreds of years would require sophisticated genetic monitoring and intervention, perhaps even a genetic library of stored sperm and egg samples, raising complex ethical questions about human reproduction and engineering. The social and psychological implications of a multi-generational voyage are arguably even more profound and less predictable than the technical challenges. Imagine a society born and living its entire existence within the confines of a metallic shell, never experiencing a natural sky, a fresh breeze, or the vast open spaces of a planetary surface. The psychological toll of such intense lifelong confinement, divorced from the natural world, could be immense. Issues of cabin fever, chronic stress, sensory deprivation, and existential ennui could become pervasive, leading to widespread mental health crises, apathy, or even violent unrest. How would human psychology adapt to a reality where the only horizon is an artificial one, and the only nature is a carefully curated, fragile ecosystem? Perhaps the most critical challenge lies in maintaining the original mission's purpose and motivation across centuries. The initial crew would be driven by the grand ambition of reaching Proxima Centauri b, a dream they consciously chose to pursue. But for the 10th, or 20th, or 50th generation born into the ship, the mission is not a choice but an inheritance, a predetermined destiny. What if these later generations lose sight of the original goal, or worse, actively rebel against it? The why of their existence could become blurred, lost to the mists of time and the accumulating grievances of a closed society. Could they decide to abandon the mission, turn back, or simply settle for the first vaguely habitable asteroid they encounter? The concept of a generational contract, where one generation commits future unborn generations to an incredibly difficult and dangerous task, carries immense ethical weight and is rife with potential for conflict and disillusionment. Social stability within such a confined, isolated community would be constantly tested. How would governance evolve over centuries? Would a hierarchical structure, necessary for mission control, transform into an oppressive regime? Would factions emerge based on genetic lineage, specialized skills, or philosophical differences about the mission's purpose, resource allocation, power struggles, and the enforcement of laws in a closed system with nowhere to escape would be fertile ground for social breakdown. The very definition of humanity might shift as generations grow increasingly distinct from their earthbound ancestors, developing their own unique cultures, languages, and even physical adaptations to their artificial environment. This social evolution, while fascinating to contemplate, introduces unpredictable variables that could easily derail a mission spanning centuries. The logistical nightmare of a generation ship extends beyond biology and sociology. Every piece of equipment, every tool, every raw material brought from Earth or produced internally would be a finite resource. The ship itself, after decades of operation, would require continuous maintenance, repairs, and upgrades. This demands not only a constant supply of spare parts and raw materials, but also a continuous pipeline of highly skilled engineers, technicians, and scientists trained over generations to understand and maintain increasingly ancient and complex systems. What happens when a crucial, irreplaceable component fails after 300 years? How do you mine for rare elements or manufacture advanced microprocessors in the vacuum of deep space? The reliance on a closed system for both biological and technological renewal is a monumental undertaking, fraught with opportunities for catastrophic failure. Ultimately, the generation ship dilemma reveals that Proxima Centauri b is not merely protected by physical barriers, but by human ones. Even if the engineering impossible could be overcome, the challenges of maintaining biological viability, psychological health, and social cohesion across multiple generations on a multi-century voyage are so profound that they represent an entirely different order of impossibility. It forces us to confront whether humanity, as a species, possesses the collective will, foresight, and adaptability to commit unborn generations to such an immense, uncertain odyssey, making the journey to our nearest exoplanet not just a technological dream, but a deeply challenging, perhaps even tragic human endeavour. The romantic notion of sailing through an empty, peaceful void to reach another star is a pervasive fantasy. Yet, just as the ocean depths conceal unseen currents and formidable creatures, the seemingly serene expanse of interstellar space harbours its own insidious dangers. It is not an empty vacuum, but a sparse, turbulent medium, where even microscopic particles become lethal projectiles, posing a constant existential threat to any craft daring to traverse the 4.2 light-years to Proxima Centauri b. This microscopic threat, often underestimated, adds yet another layer to the engineering impossible. The interstellar medium, or ISM, is the sparse matter and radiation that exists between star systems within a galaxy. While it is orders of magnitude less dense than any vacuum we can create on Earth, typically only a few atoms per cubic centimetre, it is far from truly empty. It is a cosmic soup composed primarily of hydrogen and helium gas, but also containing trace amounts of dust grains, plasma, and various forms of radiation. These dust grains, the silent, omnipresent menace, are typically sub-micrometer in size, comparable to smoke particles or fine terrestrial dust. On Earth, or even orbiting within our solar system at conventional speeds, encountering such a particle would be utterly harmless, barely registering as a blip. However, the dynamics of impact change catastrophically when a spacecraft is hurtling through space. Let us consider a hypothetical interstellar probe, optimized for speed, traveling at just 1/10 the speed of light, or 0.1 c. This translates to an astonishing 30,000 kilometers per second. At such velocities, the kinetic energy carried by even a minuscule particle becomes immense, transforming a speck of dust into a hypervelocity bullet, an object of unimaginable destructive potential. To illustrate this, consider the fundamental physics of kinetic energy. E, 1 + 2 mv2. The energy scales with the mass of the object, but, crucially, it scales with the square of its velocity. This means that a small increase in speed leads to a disproportionately massive increase in destructive power. A single dust grain, perhaps only a millionth of a gram, hitting a spacecraft at 0.1 c would possess kinetic energy equivalent to that of a high-velocity rifle bullet, or even a small hand grenade detonating on the hull. Scale this up to a milligram-sized particle, and the impact energy becomes comparable to a meteoroid strike or even a small car travelling at highway speeds. At the extreme relativistic speeds required for a multi-decade journey, even a single atom impacting the spacecraft at near light speed can produce a localized plasma explosion. The consequences of such impacts are devastating. Traditional spacecraft shielding, like the multi-layered Whipple shields used to protect against micrometeoroids in Earth orbit, are designed for impacts at speeds of tens of kilometers per second. While effective against larger, slower objects by vaporizing them over multiple layers, they are utterly inadequate against hypervelocity interstellar dust. At 0.1 c, a dust grain wouldn't simply vaporize, it would punch a clean, high-velocity hole through multiple layers of even advanced armor, creating a localized explosion and a shockwave that propagates through the structure. A single such impact could lead to rapid depressurization of habitat modules, compromising life support. It could sever critical electrical conduits, causing system failures in navigation, communication, or propulsion. Fuel tanks could rupture, leading to catastrophic explosions. Sensitive scientific instruments, vital for mission success, would be instantly destroyed. Even if the impact doesn't cause immediate total destruction, the cumulative effect of countless microscopic abrasions over decades would erode the spacecraft's exterior, degrading critical sensors, solar panels, and radiating surfaces, slowly stripping away its functionality and integrity. The journey to Proxima Centauri b is not a clean, unobstructed flight. It is a relentless gauntlet, a slow pulverization by an invisible enemy, and the threat isn't limited to mere dust. While incredibly rare, interstellar space is also home to larger, more substantial objects. The recent detections of Oumuamua and 2I Borisov, the first confirmed interstellar objects to pass through our solar system, unequivocally demonstrate that macroscopic debris, asteroids, comets, or even fragments of rogue planets, regularly traverse the void between stars. These objects, travelling at their own interstellar velocities, represent an entirely different order of hazard. While the probability of encountering one is exceedingly low, over a journey spanning 40 trillion kilometers and decades of travel, this minute probability is not zero. A collision with even a pebble-sized object at relativistic speeds would be instantly catastrophic, vaporizing the spacecraft and its contents into a cloud of plasma. No amount of practical shielding could withstand such an event. The vastness of space becomes a cosmic minefield, where even the rarest of hazards looms as an absolute end to the mission. Beyond these tangible forms of matter, the cosmos holds other, more theoretical and profoundly unsettling unknown phenomena that could jeopardize interstellar travel. The universe is a place of unfathomable complexity, and our current understanding, while vast, is far from complete. What if there are regions of space with anomalous energy fields, previously undetected pockets of exotic matter, or even subtle quantum phenomena that only manifest over immense distances or at extreme velocities? For instance, the existence of primordial black holes, theoretical relics from the early universe, remains unconfirmed. If even a small population of these dark, incredibly dense objects exists, silently wandering through interstellar space, an unexpected encounter could lead to gravitational perturbations that throw a spacecraft off course, or, in the worst case, a direct collision. These objects are virtually invisible, making detection almost impossible until a spacecraft is already in their gravitational grip. Then there are the unknown unknowns, the unforeseen forces or particles that our current physics models haven't yet accounted for. As we push the boundaries of exploration, we invariably encounter phenomena that challenge our established understanding. Could there be strange fluctuations in space-time, unforeseen interactions with dark matter or dark energy, or subtle instabilities in the fabric of reality itself that only become apparent when traversing such immense, untouched cosmic distances? While speculative, the history of science is replete with examples of unexpected discoveries altering fundamental assumptions. An interstellar journey represents a venture into truly uncharted territory, where the rules might bend in ways we cannot yet predict. In summary, the notion that interstellar space is a pristine, empty pathway is a dangerous misconception. From the ceaseless barrage of hypervelocity dust grains that erode and puncture, to the rare but utterly catastrophic impact of larger interstellar objects, and the potential for unknown cosmic phenomena, the journey to Proxima Centauri b is fraught with peril. This invisible, microscopic, and sometimes theoretical threat demands levels of resilience, redundancy, and predictive capability in spacecraft design that currently exist only in the realm of science fiction. Proxima Centauri b remains guarded not just by distance, stellar fury, and the limits of engineering, but by the very particles that drift through the seemingly vacant expanse, a silent, deadly cosmic gauntlet. The relentless barrage of interstellar radiation and the microscopic cosmic debris, though invisible, paint a stark picture of the universe's inherent hostility. They underscore that even if we could endure the generational voyages, the very fabric of space presents a gauntlet of dangers. Yet, for many, these formidable obstacles only fuel a deeper yearning, a persistent dream whispered in the halls of science fiction, to transcend the cosmic speed limit, to bend the very rules of reality, and to reach distant stars like Proxima Centauri b in a flash, not a crawl. This is the allure of the warp drive, the wormhole, and other concepts that promise faster than light, or FTL, travel, a dream that, upon closer scientific scrutiny, reveals itself to be an even more profound impossibility, demanding not just new engineering, but a complete rewriting of the fundamental laws of physics. The most widely discussed and theoretically plausible of these FTL concepts is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, inspired by the Star Trek universe. Alcubierre mathematically demonstrated that a spacecraft could theoretically achieve faster-than-light travel without actually moving faster than light locally. The ingenuity lies in manipulating spacetime itself. Imagine a ship encased within a warp bubble, a region of spacetime where space in front of the ship is contracted or squeezed, and space behind it is expanded or stretched. The ship itself would remain stationary within its local warp bubble, not exceeding the speed of light relative to its immediate surroundings. It's not the ship moving through space, but space itself moving around the ship, like a surfer riding a wave. This elegant solution seemingly bypasses Einstein's speed limit, as it's the fabric of the universe, not matter. That's exceeding light speed. The theoretical framework for the Alcubierre drive is rooted in Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Alcubierre showed that if one could create the right kind of space-time curvature, a region could effectively travel faster than light relative to distant observers. This isn't a violation of relativity. It's an exploitation of its more exotic solutions. The appeal is immediate. If achievable, a warp drive could theoretically allow a journey to Proxima Centauri b in mere days or weeks, rendering all the previously discussed problems of duration, radiation accumulation, and generational ships utterly moot. The nearest exoplanet would truly become a neighbour, not a distant dream. However, the elegant mathematical solution hides a gargantuan physical hurdle: the requirement for exotic matter. To create the space-time distortions necessary for a warp bubble, specifically to contract space in front and expand it behind, Alcubierre's equations mandate the existence of matter with negative energy density. To clarify, all known forms of matter and energy have positive mass and positive energy density. Exotic matter, on the other hand, would possess characteristics like negative mass or negative pressure, behaving in ways that defy our everyday experience and current experimental observations. While certain quantum phenomena, such as the Casimir effect, hint at localized regions of negative energy, these are minuscule, transient, and far from the stable, macroscopic quantities required to generate a warp bubble large enough for a spacecraft. The exotic matter problem isn't a mere engineering challenge, it's a fundamental crisis in physics. We do not know if such matter exists, or if it can be created or harnessed in any meaningful quantity. If it doesn't exist, the Alcubierre drive remains a mathematical curiosity, a thought experiment without physical foundation. Even if exotic matter were somehow discovered or synthesized, the amount required to create a stable warp bubble around a human-sized spacecraft is utterly astronomical. Initial calculations by Alcubierre suggested an amount of exotic matter equivalent to the mass of Jupiter. Subsequent refinements by other physicists have somewhat reduced this, but even the most optimistic estimates still demand a quantity of negative energy equivalent to several times the mass of our Sun or more. To put this into perspective, generating such an immense amount of energy, even if it's negative, or creating such a vast quantity of hypothetical exotic matter is far beyond any known physical process or technological capability. It would require dismantling entire stars or harnessing cosmic forces on a scale that beggars belief. Power plant. It's a requirement for a power source that literally does not exist and potentially cannot exist within the known universe. Furthermore, the Alcubierre drive presents a host of other profound, unsettling paradoxes and practical impossibilities. One major concern is causality violation. If FTL travel were possible, even by warping space-time, it could potentially allow for information or even matter to be sent to the past, leading to grandfather paradoxes and fundamentally undermining the cause and effect structure of reality. Most physicists consider such violations to be strong indicators that FTL mechanisms, even theoretical ones, are fundamentally flawed or prohibited by deeper physical principles. Then there is the issue of what lies outside the warp bubble. As space is compressed in front of the ship, any matter or radiation within that region would accumulate, essentially forming a super-energetic, forward-moving wall of particles. Upon deceleration and the collapse of the warp bubble, this accumulated energy and matter would be released as an unimaginably powerful, focused burst of radiation, a catastrophic shockwave that would instantly destroy anything at the destination, including Proxima Centauri b, rendering any exploratory mission utterly self-defeating. The very act of arrival would be an act of annihilation. Moreover, steering or even turning off an Alcubierre drive presents its own set of problems. The ship within the warp bubble might be causally disconnected from the space-time outside of it, effectively creating a kind of event horizon. This means the crew might not be able to interact with or even perceive the external universe, making navigation impossible. How would they know where they are going, or when to stop, if they cannot observe their surroundings? And if the drive cannot be turned off from within, the ship could become an uncontrollable projectile trapped in its own space-time distortion. Some physicists even speculate that the intense space-time curvature itself could generate a torrent of Hawking-like radiation, boiling the crew alive inside the bubble. Beyond warp drives, another staple of science fiction for bypassing cosmic distances is the wormhole. Mathematically, wormholes are hypothetical tunnels or shortcuts through space-time, connecting two distant points in the universe, or even two different universes. They are often visualized as a bridge connecting two separate regions of space-time, allowing for near instantaneous travel between them. Just imagine stepping into one end of a cosmic tunnel near Earth, and instantly emerging near Proxima Centauri b. However, wormholes, like warp drives, are plagued by similar and even greater physical challenges. While general relativity allows for the theoretical existence of wormholes, any traversable wormhole, one large enough and stable enough for a ship to pass through, would also require enormous quantities of exotic matter. With negative energy density to keep its throat open, without this exotic matter a wormhole would be inherently unstable, collapsing faster than light could traverse it, crushing anything attempting to pass through. The extreme gravitational forces at the mouth of a wormhole, even if stable, could also rip apart any object attempting to enter. Furthermore, creating a wormhole of sufficient size and stability, and then precisely positioning its exit point at a desired destination, like Proxima Centauri b, is an engineering feat that borders on magical. In essence, these concepts, the warp drive and wormholes, are not merely advanced technological challenges. They demand a profound and revolutionary paradigm shift in our understanding of physics. They require either the discovery of matter and energy that defies all known properties, or a fundamental revision of the laws of space-time and causality as laid out by Einstein, until such time as exotic matter is proven to exist and harnessed on an unprecedented scale, or new theories emerge that gracefully integrate FTL travel without violating the very consistency of the universe. These solutions remain captivating dreams. They offer hope, but demand miracles that fundamentally rewrite the cosmic rulebook, solidifying Proxima Centauri b's status as unreachable through such means. The dream of planting a flag on Proxima Centauri b, of touching the soil of another star system, remains a potent symbol of human ambition. It is a whisper of possibility that echoes through our collective imagination, fueling visions of a future where humanity is not confined to a single world, but is a truly interstellar species. Yet, as our intellectual journey through the scientific realities of interstellar travel has revealed, this tantalizing proximity is ultimately a cruel illusion, a celestial siren call that beckons from across a chasm of profound, unyielding barriers. Proxima Centauri b is not merely 4.2 light-years away, it is a universe away, guarded not just by cosmic distance, but by the very fabric of physical law and the relentless indifference of the cosmos. We began with the seemingly simple number, 4.2 light-years, but this figure, so easily uttered, hides a chasm of 40 trillion kilometers, a stretch of emptiness that transforms a celestial neighbor into an astronomical eternity. Our fastest spacecraft, launched decades ago, would require 75,000 years to merely drift to this star system, a duration longer than the entire recorded history of human civilization. To compress this journey into a human timescale demands velocities that defy our current engineering, confronting us with the tyranny of the rocket equation, where the energy required to accelerate a ship to a significant fraction of light speed would dwarf the entire energy output of our planet. This isn't just a matter of designing a better engine, mass, energy, and the ultimate cosmic speed limit. Even if a miracle of propulsion could propel us across that void, the destination itself offers a hostile welcome. Proxima Centauri, a red dwarf, is not the benign sun we might imagine. It is a star prone to violent, frequent and powerful flares, spewing torrents of X-ray and ultraviolet radiation, along with high-energy charged particles. A planet as close as Proxima b, lacking the thick protective atmosphere and robust magnetic field of Earth, would be subjected to continuous atmospheric stripping and surface sterilization. Any form of complex life, as we know it, would struggle to endure, let alone thrive, in such a perpetually irradiated environment, likely requiring refuge deep beneath the planet's surface. Adding to this stellar fury is the profound impact of tidal locking. Proxima b is gravitationally shackled to its star, presenting one face in perpetual scorching daylight and the other in eternal cryogenic darkness. Between these two extremes lies a narrow terminator zone, often envisioned as the sole potential refuge for liquid water. Yet, this zone would be a battleground of unimaginable meteorological violence, where super hurricanes, driven by the colossal temperature differential, would ceaselessly scour the landscape. Such a planet is not a serene haven, but a world of absolute unyielding extremes, making stable surface conditions for life or human settlement a near impossibility. The journey itself, even before arrival, would be a gauntlet of invisible killers. The seemingly empty void of interstellar space is a sparse but deadly soup of galactic cosmic rays. high-energy particles accelerated by supernovae and black holes to near-light speed. These microscopic bullets would relentlessly bombard any spacecraft, causing irreparable damage to electronics and inflicting devastating, cumulative genetic and physiological harm to any human crew over decades of exposure. Traditional shielding is inadequate, and even theoretical active shields demand power sources far beyond our current capabilities. Compounding this is the threat of hypervelocity dust and rare but catastrophic larger interstellar objects, transforming the cosmic highway into a minefield where these physical barriers culminate in the engineering impossible. Our most advanced theoretical propulsion systems, fusion drives, antimatter rockets, Bussard ramjets, each encounter fundamental scientific and logistical hurdles that render them impractical, if not outright fantastical. Fusion remains elusive on Earth. Antimatter production and storage are currently picogram-scale endeavours that require astronomical energy input, and ramjets demand gargantuan drag-inducing scoops to collect incredibly sparse interstellar fuel. These are not mere technical challenges solvable with ingenuity. They are problems that push against the very boundaries of known physics, demanding breakthroughs that would fundamentally rewrite our understanding of matter and energy. And if these engineering feats were somehow overcome, the human element emerges as the final, most poignant barrier. The concept of a generation ship designed to traverse the cosmos over centuries places an unbearable burden on human biology, psychology, and social cohesion. Genetic degradation from continuous radiation, the perils of a limited gene pool, and the psychological toll of lifelong confinement in an artificial environment pose profound risks to the very survival and sanity of the crew. More critically, how would the mission's original purpose be maintained across dozens of generations, born into a destiny they did not choose? The social and ethical complexities of such an undertaking are as profound as the physical ones, making the success of a multi-generational voyage a gamble of unprecedented scale. Finally, the alluring promise of faster-than-light travel, embodied by concepts like the Alcubierre warp drive or traversable wormholes, while mathematically intriguing, demands the existence of exotic matter with negative energy density, a substance that has never been observed and may not even exist. Even if it did, the quantities required are astronomical, dwarfing the mass of entire stars, and the theoretical side effects such as causal paradoxes or catastrophic energy release upon arrival render such solutions more destructive than beneficial. These FTL concepts are not just difficult, they are currently considered impossible within the framework of consistent physics, pushing them into the realm of pure fantasy. Thus, the dream of reaching Proxima Centauri b, our seemingly closest stellar kin, is shattered by a constellation of profound, interlinked impossibilities. This apparent defeat, however, is not a surrender. It is a profound revelation. It forces us to redefine what exploration means. If direct physical visitation is beyond our grasp, then the true frontier lies not in conquest, but in comprehension. Our journey to Proxima b, though purely intellectual, has taught us invaluable lessons about the scale of the universe, the limits of our technology, and the astonishing fragility and uniqueness of our own planet. The very act of contemplating these barriers refines our understanding of humanity's place in the vast cosmic tapestry. We are not yet cosmic travellers, but we are cosmic thinkers. We are beings capable of peering across 4.2 light-years, decoding the faint whispers of light from a distant star, and inferring the existence of worlds we can only dream of touching. This capacity for remote understanding, for theoretical exploration, for building models of impossible journeys, is a testament to the power of the human mind. The unreachable stars inspire us not to touch them physically, but to understand them intellectually, to unravel the cosmic laws that govern their existence and our own. Perhaps the greatest lesson from Proxima Centauri b is a renewed appreciation for Earth. Our pale blue dot, with its nurturing atmosphere, its stable star, its life-sustaining water, and its hospitable rotation, is not just a planet among billions. It is a precious singular haven, a cosmic anomaly of incredible rarity. The formidable barriers to interstellar travel underscore the immense value of the home we already possess, urging us to cherish and protect it, with a fervour equal to our desire for distant horizons. The quest to reach Proxima Centauri b may be futile in a physical sense, but the questions it raises continue to propel science forward, It challenges us to push the boundaries of materials, science, energy generation, and theoretical physics. It forces us to grapple with profound philosophical dilemmas about humanity's long-term future, our ethical responsibilities to potential future generations, and the very definition of exploration. The true frontier may not be out there, among the distant stars, but within the depths of our own scientific inquiry, our collective imagination, and our evolving understanding of the fundamental laws that govern all of existence. As we continue to observe Proxima Centauri b from afar, gathering more data through increasingly powerful telescopes, we are not merely looking at an exoplanet. We are looking at a mirror. It reflects our boundless ambition, our technological limitations, and our enduring, insatiable hunger for knowledge. The stars are not waiting for us to visit, but to inspire us to comprehend, to deepen our perspective, and to remind us that the most profound journeys are often those taken not with rockets, but with the mind.